If I just make sure it will show up on the correct screen, here we are. Right. So again, the reason why we are going through these topics and also the order that we're going through them is pretty much this here. So as discussed previously, basically the building blocks for all modern sane programming languages work the same way, and they can be deconstructed to these elements. And basically at this point we have already covered variables and data types. We've covered inputs and outputs, conditionals, repetitions, functions, and the only thing that's left on this list are the abstract and compound data types. And abstract and compound data types might sound difficult and a complex topic, but I assure you they are not. They are fairly easy to grasp and very intuitive. Okay. So when we talk about composite data structures, what is it that we actually mean? So they're not actually a new thing. We have come across them previously on the course, because we have, of course, seen, well, strings or strings of text. So remember how an individual string of text is just a collection of individual letters. Well, that's basically how we define a composite data structure. So a string is a collection of individual letters, and in general, we would say a composite structure is a collection of things. So we have some things, not necessarily letters anymore, but just a collection of things. For example, a collection of numbers, collection of letters, or weirdly enough, of words, collection of books, collection of something that go together. The same way in real life, for example, a library would be a collection of individual books, and a book is a collection of individual pages, and a page is a collection of individual words. So in this sense, the composite data structure is nothing that spectacular, and nothing that we haven't covered before. So if you remember how the strings of text work, I think we covered them on in a lot of detail during the third lesson in the series. So you remember that we have these individual letters that form what is called a string, and we could use these indexes to represent where each letter is placed in this string of text. And if we were to depict it this way as a table, we could see that one letter fits very nicely inside one column in this table. And these respective numbers from 0 to 4 then represent the distance between the beginning of the word to that individual letter. Well, these collections in Python, they can be virtually anything, but this collection of letters in a word is a really easy example to begin with. You might be thinking, okay, how do you actually know something is a composite structure? Well, it's easy. When you see a collection of things that you can access the individual elements using these indexes or slices, or it's something you can go through in a for loop, then we're talking about something that is a composite structure. So just to recap, if we were to have a simple example of a collection, and I'm going to use the same example. So as an example of a collection, I'm going to be using a string of text, which of course is composed of individual letters. Individual letters. So, and indeed, we can go through this collection using the for loop. So I might say something like for letter in a word, and then I do something with this individual letter that I pick out from this word. For example, just print it on the screen like that. And finally, running this piece of code will give me each individual letter of this word neatly one on each line. So that is basically what we're talking about here. So a collection of things, and you can go through these individual things in a collection using this for loop. Usually the string is not the easiest collection to start with, because it can only do so many things. So many things, those individual words, individual sentences, or individual strings of text. They are just inanimate collections of letters that don't really do anything. So probably we would want a more versatile example of what a composite data structure might actually do. And a good example of this is a list. And a list is a good example for two reasons. First of all, because, well, the name of the data structure is called list, and it pretty well it gives a pretty good example of how all of the data structures actually work. Secondly, the list is pretty descriptive as a name, because indeed we are talking about something that's a list. So a collection of things. You might have a shopping list, or Schindler's list, or whatever list you might think of. So really, a collection of different items on a list is the best example that I can come up with here. Something about the syntax. So a list is denoted with this special syntax that involves using the square brackets. And items within a list are separated using a comma. So if we were to, for example, I'm going to pull up the editor window once again. This example we do not need anymore, so I'm just going to comment it out and just move it out of sight. So for example, we might have a list. Let's call it a shopping list. And as said, the list is written using this special syntax having to do with the square brackets. And inside we can have different elements, items on this shopping list. So let's say we bring milk from the shop, and maybe maybe bread as well. And again, the items on this list need to be separated using a comma. And this is rather important, that the comma separates the items on the list, because, well, as you may remember, the decimal separator in Python is a dot and not the comma, and this is the reason why. So the reason, even though in many European languages the comma is used for separating decimal points within a number, it's not used in this meaning in this programming language because it has another meaning. It's used to separate items in collections. So now you know why the decimal separator is a dot and not the comma. The contents of a list can then be accessed either by iterating through the list or using the individual list indexes. And if we were to want to get a number of items on the list, we can use a special function called len, and len stands for length. And we have already seen this function in practice when we were playing with the strings of text in lesson 3. So to demonstrate that, let's take a look at at our list now that we have covered all the basics. So we have a elementary shopping list here. And the first thing we could do is simply print the contents of this list. We can actually do that in a couple of different ways. So first of all, I could just say, okay, let's hand the shopping list to the print function and just see what comes out. And print can handle a lot of different things by default, so we don't actually have to specify anything else. All you have to say is we want to print the shopping list, and the contents of the shopping list that are placed within these square brackets come out. We can also get the number of items on the list by using the len function like this. So now that if I run the code, we should get the contents and also how many items are on this list. So indeed, contents here, milk and bread, and 2 items add up to exactly 2. So even though the list is 0 indexed, as I'm sure you remember from the earlier lessons with the strings, the number of items on the list, or the number of characters in a word, of course, doesn't change. So the list itself, this would be the 0th element on the list, but in total there are 2. Speaking of the 0th element on the list, if we want to access the individual elements, we can just refer to them based on their index number. So if I say I want to take the first element or 0th element on the shopping list and just print it, I can do it like this. And the same, of course, goes with the rest of the items. So if I want the second element, I just want the element that's at number 1 on this list, and the same works. Of course, here you have to be careful not to exceed the limits of this list. So if I wanted the element that's at at position number 2, which is the 3rd element on this list that only contains 2 things, you will find that this does not work. So there isn't a 3rd element, there isn't an element at list in the index number 2, so we get an error instead. So we get specifically an index error there telling us that our list index is out of range, which is pretty descriptive because that is exactly what's going on here. So we can't refer to this item because it does not exist. This list only has 2 elements. So if we have elements 0 and 1, there cannot be referring to element number 2 doesn't make any sense. So again, this going through the individual items, sure you can do this, and in sometimes it makes sense to do this. We can also go through all the elements, as said, using the for loop. So we might say something like for element in shopping list, and then we print the individual elements here. So now we should get the first line, the entire list here, the length of it, and then the individual elements should follow, which you can see here. So that's the entire list, that's the length of the list, and those are the individual elements at the end here. So you see they pop up as their own on their own row, because this print function here takes each individual element from this list and prints them individually. Okay, so far so good, but we're only looking at the contents on this list we have hard coded here. That means that this list that we have been looking at is more or less static. It only contains the elements that we defined within those square brackets and within our program code. Now, the thing here is that we can also add and remove items dynamically, meaning we should be able to add and remove items while the program is running. And to do that, we can use special functions called list.append and list.remove. And these functions are special because they are named a bit differently. So they use what is called a dot notation, which means that we add the name of this function to the end of the list name with using a dot. So for example, if I wanted to use append to add an element on our shopping list, that would be done somewhat like this. So we have here gone through the elements on the list. Then I take the shopping list once again, and I call the use the special function append, and then add another item on the list like that. And afterwards, if I print the contents of the shopping list once again, we should be able to see this one extra element there that we just added. So as we can see from the beginning, we only had milk and bread. At the end, after this append function has been called, we have milk and bread and also a pineapple. It's fairly straightforward. Remove works the same way. So if we wanted to remove an element from the list, we just call this special dot remove function here, and we give some value. Let's say we want to remove milk altogether from this shopping list, and once again just print the contents of the list here. So now if we run it, we can see we started out with milk and bread. After adding a pineapple, we had milk and bread and a pineapple on the list. And finally, after removing milk, we only end up with bread and a pineapple. These append and remove functions are pretty straightforward to use. The only danger here is if you were to try to remove an element that doesn't exist on the list. So for example, if I instead of milk I try to remove peanut butter from our shopping list, this is going to give us another error saying this element that we wanted is not on the list, because indeed we have not added peanut butter on the list, so the interpreter doesn't know what to do, so it gives us an error. So just a word of warning here, but otherwise these are fairly self-evident how they work. These append and remove functions are especially useful if we need to ask the user for what we should put in the list. So here we might do something like the following, and I'm just gonna bring up the editor here once more to complete this example one piece at a time. Okay, so we should start with again the shopping list. And this time I'm not going to add any elements on it. I'm simply going to use the square brackets here, but not put any items inside it, because this is perfectly legitimate. It just means we have a variable that points to this list, and the list happens to be empty. So if we were to print the contents of this list right now, if we were to print the content of this list right now, we will see that the list is indeed empty. There is nothing inside those square brackets. Anyway, so in order to put something in that list, we need to do something. So let's create a small loop where we ask for items to be added on the list. So let's say that while true, because we don't know how many items are going to end up on the list. So probably while true makes sense. We ask for some user input. So we say, item comes from the user, and we ask the user to add a new item to the list. And what we do with this item, we simply take the shopping list and append this item at the end of it, like so. And presumably at the end, we just want to show what the items are on the shopping list. So you might say something like items on the shopping list. In list are, and then just the contents of the list as well. And again, you can just give the shopping list to the print function if you don't care about the square brackets in the printing here. And in this case, we don't really care about them. Something to remember at this point when we're doing it like this is, of course, so how does this while loop know when to stop? So we haven't specified any end condition, so we probably should do that to be safe. So let's just say here as a rule that we use 0 as a signal to stop. Here we are. And of course, we need some conditional to check if that end condition happens. So if the item happens to be 0, then we break out of the loop. And only if we don't break out of the loop, we add the item to the shopping list. Okay, let's try this in practice. So we're being prompted to add some items on the shopping list. So let's put some milk, some eggs, and maybe bananas. Let's say we're making a banana pancake, and I think that's enough. So we end it with 0. And as you can see, items on the shopping list now are milk and some bananas. Okay, seems to work, and this might already have some real world application. So if you were to make your own shopping list itinerary app this might be the logic behind the curtains, how it actually works. So we have some sort of list, some sort of collection in which we are putting items into. Let's continue this idea. So let's at the end give the user a chance to actually remove something. So maybe we have we have changed our mind about something on the list. So let's ask for user input again. And let's say that again 0 is a signal for stop or no. And then we do some pretty much the opposite. So if we don't want to remove anything, so if this if we don't want to remove anything, we shouldn't do anything. So only if this item happens to be not 0, then we should take the shopping list and remove something from it. And that should pretty much be it. So only if we don't, if in all cases when we type in 0, we're going to just ignore this line, because if to remove is not equal to 0, that's the only condition in which we remove something. And in all other cases, when we have actually typed something in, then we try to remove something from the list. And finally, we might just copy this line to the end, so we can see what the shopping list, how the shopping list looks like at the end of this program. So should work pretty identically to the previous iteration, except now we just added this functionality to remove something on the go. So let's take a look. So again, let's add milk and eggs and some bananas. And I think that's it. And at that time, the items on our shopping list are milk and eggs and bananas. If we want to remove something, let's say we want an eggless pancake. We type in eggs, and then we end up with a shopping list containing milk and bananas. So that should pretty much illustrate how the append and remove functions work. Something about append and remove, what they actually are. So that's how they work, but what are they really? They are these special functions that are actually called methods in programming lingo. So adding this dot append or dot remove to the list's name is a way of invoking a special function that's tied to this particular list. And actually, it turns out that lists contain a lot of these special functions. You can find a full list at this address, which is basically just points to the Python version 3 documentation. But basically, append and remove are those that you will need in practice. So if you were to want to look at this, you can see that indeed there are a lot of these special functions, methods that you could use. Append is there. There's also something called extend. There's also something called insert. You can see remove there. There's also pop and a bunch of other special functions, methods that exist, but we don't really need to go that deep into detail. Just know that they exist there, and if you are looking for some special functionality, that is where you should head your browser to. Some of these other methods may be useful though. So there are 4 that I have listed here. There's clear, which removes all elements from a list. There is count, that counts how many times one element appears on a list. Reverse is the order of the list. And sorts the list into numerical or alphabetical order. So to give an example of how those 4 work, I'm going to bring up the interpreter and not the code editor this time. So let's create a quick list that I'm just going to call L for that. It's going to be short for list. Just going to let's continue with the idea of having a shopping list. So let's put there bananas, apples, and some pears maybe. And what else might we have? Kiwi fruits maybe. Okay, so then we have a shopping list containing some fruits. So of course this is not in alphabetical order. So saying something like L dot sort. This should sort the list into alphabetical order. So if we look at the order of it now, the items have switched place. So now it's in alphabetical order. Reverse is the order. So now they should be in reverse alphabetical order, which you can see they are. If you wanted to look at how many kiwi fruits you have on your shopping list, that's done with count. And of course, clear empties the entire list, meaning that at the end, the list is completely empty. Then, in addition to these specific, very special methods, functions that work with the lists and the lists only, there happens to be some generic functions that work with lists as well. So these are functions that are not called with this special dot notation. These are just functions that you call and you give the list that you want to work with as a parameter to these functions. So previously we have used len for to get the length of some collection. So this is an example of what these generic functions might be. So len indeed is an example of a generic function that also works with a list. There are some other generic functions. For example, max, min, and sum. So max returns you the maximum value of a list, min returns you the minimum value of a list, and sum gives you the sum of all the elements on the list. And probably these are most useful with lists that contain numbers. That's not to say you can't use them with lists that have other things besides numbers. It will give you some result. It might just not be one that you expect it to be. So probably this is most useful with numbers only. So to give an example of that, let's redefine this list called L into something with numbers. So let's say it's going to contain numbers from 1 to 5. So again, just asking what the list contains, we can see indeed it has the numbers from 1 to 5. We can use any of the previously mentioned list methods for this list as well, even though it's not a shopping list anymore, it's a list of numbers. And it should do the same thing. So for example, reverse is the order of the list. So nothing new here. Then there are these general functions listed here. So for example, the most useful probably is len, which gives you the length, how many items are on this list. Max gives you the highest number on the list. Min gives you the lowest. And sum gives you the sum of all the numbers. Interestingly, you can use sum and len together to get the average of these numbers. So if we were to do sum from this collection of numbers divided by the length of this list, we get the average, and here, since 3 happens to be the middle number there, the average of these numbers happen to be 3. I think there is one of the weekly exercises related to this chapter that has to do with counting an average. So that's a direct takeaway that you can take from here on how to calculate an average. And by average here, I of course mean the arithmetic average. There are other ways of calculating averages as well, but the most common way to calculate average is of course the arithmetic one. When working with lists, there are a couple of situations where you ought to be really careful. One of them happens to involve functions. So in the previous lesson, we talked about functions, and it turns out that when we use lists and certain other composite structures too with functions, this can sometimes cause a little bit of confusion. And to illustrate what I mean by this, we should take a code example. So again, I'm just going to make this previous example disappear. And well, let's start with looking at a simple example. So let's go back a bit to last week's topic, which was functions, to look at how functions and function parameters work. So let's first of all create a simple variable. Let's call it number, and let's put some random number inside this variable. And then let's also create a function. I'm just going to call it, let's call it function1 or fun1. And I'm just going to make it so that it takes in one parameter. And let's say this parameter is going to be a number. And what it's going to do with this number is change its value to some random number. So here I'm just going to use 24, which is basically the reverse of 42, if you like. So the idea here is that, of course, if I call this function and I give it this variable, which now is set to 42 as a parameter, it's going to receive this number 42 as a parameter, and then it's going to change this number into 24 instead. And at the end, if we look at what the value of this number is, we're going to find out if this function managed to change the value of this number or not. So if I run it now, we will see. Of course, it was called fun1 and not just fun. Okay, here we are. So we're going to see that even though we passed this variable number here to this function, which is supposed to change its value, and at the end we try to print its real value here, we see it remains unchanged. Now, if you remember, this has to do with the scope of variables. So this function num here only exists within the scope of this function. So therefore, nothing that happens within this function has any effect for the scope that is outside of the function, which happens to be right here. So even though we pass this variable as a parameter to this function, and this function tries to change the value of that parameter, it's going to do that within the scope of this function. If we look at what the value for this num is here, and we run the code, we see that first when we are calling this function, we see that this value is 24, as we can see here. But at the end, when we return back to here to the main program, then number is of course again 42. So this is just a recap of what scope means. So you can't expect the variables that exist here on the main code level. You can't expect changes to happen to them if those changes happen in the scope of the functions, unless of course you are using a global variable, which again was strongly discouraged on this course. So this is basically what should happen. You set a value for a variable here, and no matter where you put it in which function you put it into, the value of that number really does not change apart from the time when it is being handled here within this function. Now, if we change this a little bit, let's create a function that's going to be otherwise identical. But instead of a number, I'm gonna give it a some sort of list as a parameter. And what I might do with this list, so list X, I want to change its contents, so I want to add something to it. And let's figure out later what it should do. So I'm just going to delete some of these lines. So let's say our list is going to be a list of famous Finnish things. So we're going to have a list that contains everything that happens to be from Finland and is famous. So we might have the capital city of Helsinki. We might have the fabrics from Marimekko. And then if I wanted to add something to this list, we might use something else that's very Finnish and very famous, such as the Moomins. So if I have this list here, and then I call this other function fun2, we using this list, and at the end take a look at what stuff is actually going to be or going to end up on the list. This may be different from the previous example, because what happens now is that we start with this variable, this list here. This list has 2 items. Then we pass this list that has 2 items to this function that then modifies this list, and then we come back to the main program here, and we print the whatever happens to be on this list. And as you remember from the previous time that we tried to do this, if you have a variable here in the main program, you cannot change it within this function. The remains of the previous example here are there to remind you of this. So even if you try to change the contents of some variable, it's not going to make any effect on this to the variable or to this list here in the main program. But if we look at what actually happens, at the end of the program, at this final print, we can see that this list actually does now have 3 items on it. So this function was actually able to make a change to this list that was given to it as a parameter. So clearly there is now something that's different between this function, which just took a number as a parameter, and this function that took a list as a where we gave a list as a parameter. So clearly there is something that's different between lists and some other data types, such as an integer number. Now, to explain how this works, we should take a look at a little bit of theory. So this has to do with something called mutable and immutable data types. So mutable is a property, or mutability is a property that means whether you can change the content of some variable or not. So a list is what is known as a mutable data type, meaning you can change the contents of it. You can add and remove elements, as we showed previously using the append and remove methods. Now the thing here is only these composite data types are or can even be mutable. The rest of the data types, such as the integer numbers, are immutable, meaning their contents do not change. So this is why in this example, the integer variable, when we passed it to a function that tried to change the value of it, the value in the main program didn't change, but the list then behaved differently. So we were able to add something to the list. So when we pass this list to a function, as it is a mutable type, it can be modified, whereas this immutable data type, which is the integer number, it can't. So the integers, strings, many data types well, integers, strings, and Boolean data types and floating point numbers, they are all immutable. They cannot be changed, but the list happens to be mutable and you can change the contents of it. And this can at first be very confusing, especially if we happen to be doing this. So we are using functions and we are moving from the namespace between one function to the namespace of something else, such as the main program or maybe another function. So I admit this can be very confusing, but I assure you that it's actually not. So remember how these namespaces actually work. So here we had this function that took some parameters, and then we had these values here and this function call here. So depending on where we are reading in this code, is it in this function definition and in this within this function, or is it these variable declarations here, or this function call here? There's a difference what these different variables, what the role of these different variables are, and how they handle themselves. That's basically what's going on here. So this all has to do with namespaces and local variables and global variables. So to understand what's going on here, let's take an even simpler example and look what happens when we store something in a variable. So again, backing up a little bit, let's comment this out and start with an even simpler example. So let's say we have a program and we have a variable in it. Let's call it A, and we store a random number 42 in it. Then we take another variable and store whatever is in A in it. So what happens in this code? So right now you are probably thinking it works something like this. So let's say we have the program code here. So we have program code, and then we split it from the computer memory. Like so. And so what happens when we say something like A, we should assign this number 42 to the variable A. Here, again, say A equals 42. We are doing a association between the variable A to a value of 42. Now on the next line, when we are doing this, B equals A here, what's going to happen is that the interpreter is going to look at where A is, and instead of and it's going to place the variable B here in the memory. And you might at first expect, okay, it's going to do the association like this. So it's going to associate B to A. Well, that's not exactly how it works. It's instead going to look at what A is, but then it's going to figure out where A is pointing to, and make the association and make the same kind of association to this value here. Now, what happens next should be fairly self-evident at this point, but what if we then assigned a new value for a? So we said a equals 24. Well, then what the interpreter actually does, it's going to remove this association altogether. And instead, we're going to create a new one. So the value 24 shows up in the memory, and we're just associating a with that. And of course, this is what happens in reality if we take the interpreter here for a moment and we do the same. So we say a is 42, b takes whatever value happens to be in a, like this. Then we switch a to point to some other number, and then we ask what b is. We can see that b still is pointing to this original value 42 here, because this is how the associations work. So these variables point directly to where the data is here in the computer's memory. So if we take this process and look at it again, but this time using a list as an example. So before actually drawing what's going on, let's do the same in code. So we make, for example, a as a list of a list consisting of banana and bread, again a shopping list, and then we set a b to point to wherever a is pointing. Then we change the value that a has to, for example, water and orange juice, more items that you find in a shop. And then we ask what is the value that's now stored in b, and we can see that b still points to this original list. So this works the same way for both integer numbers and lists. So we started out with a being associated to this list of a few things. There were bananas and also banana bread. Okay, I apologize for the poor handwriting, but this is really hard to do when I don't have an actual stylus pen to do it with. Then what happened next is we had this variable b, and when b is put to point to the same place where a is pointing, the association is going to be between b and this already existing list. And of course, later on, when we redefined what a is, we got rid of this association and then simply pointed a to some data structure somewhere else in the memory, like this. So everything more or less still works the same way it has. So here the key is that we are using this variable assignment, this equals operator at all times. So we're saying a equals something, b equals something, and this more or less works. But in our previous example, we used append instead. So what happens here is actually something different. So if I now pull up the interpreter and try to do the same thing. So we have A, which contains banana and bread. We point B to A again, and then we add something to A. And ask what B contains. We might be surprised that because we didn't use the variable assignment, this equals to sign here, we used append instead. Our B variable contains the same things as what this A variable contains. Now there's a very good reason for this. So again, if we think of how this code is actually executed, so on this first line here, what we do is we take A and associate it with this list here that contained some elements. Not going to type out the or try to draw the words here, but you get the picture. Then on this next line here, we have variable B, which simply finds where A is located and does the same association here. So B is associated to the same data structure. And then when we said we want to append something to A, we have simply added something here inside A. And since A and B are actually pointing to the same place, once A is changing, B changes as well. So this is important because the key difference here is that we have not redefined what A means here. We have simply appended something in the back of A. On the previous slide, we have used this equal sign here, which means we are completely redefining what A is, and then B is the only B is still left referencing this old list of things here. So if we never do this reassignment, then these two variables A and B actually end up pointing to the same place. And this is fairly important to understand because otherwise it might look that things happen randomly or that this variable assignment is something close to dark magic and spells, but it's not. It's just a question of what variables we have and where or which data elements in the computer's memory are they actually pointing to. So in this latter example, A and B point to the same thing because we are only changing the content of this existing variable, the existing data in the memory with append. So if you wanted to store something new, you would need to use the assignment operator, the equals sign. And more importantly, new data or a new list is only ever created if you use the assignment. So if you don't use an assignment, if you use append instead, it's going to modify the old list instead of creating a new one. This applies to all variables everywhere in all Python programs, but it can be especially confusing at first with functions, and that's why I am talking about it in detail and drawing these schematics of how these variables are tied to the data that's stored in the computer's memory. And again, this is not the easiest concept to wrap around, but it does work consistently, and there is nothing magical about it. Okay, so then to be a bit more confusing and to wrap up with something. Just as a reminder, the title of this lesson was Composite Data Structures and Structures in Plural. So there exists other data structures as well, in addition to the list, but we have only been talking about the list because it just, the list just demonstrates all the good qualities that all composite data structures in Python pretty much have. The other data structures include the strings, which we have already covered. There are also something called tuples and dictionaries, and I'm going to give a quick example of both before wrapping up. Then there are other data structures that include, but are not limited to, for example, objects, decks, queues, stacks, trees, and among others. But these quickly go outside the scope of a first Python programming course, so we're not going to be able to cover all of them. Strings, lists, tuples, and dictionaries you might be needing on this course. The rest are not really needed, and probably even tuples and dictionaries, their use outside of this one lesson is not going to be that critical. Pretty much everything you have to do on this course has to do with lists anyway. But just to give you the big picture of how things actually work. So as an example of another composite data structure, a tuple is almost exactly like a list, except for one key difference. When using a tuple, you cannot add or remove items after it has been initialized. So a tuple is like a list, except it does not have the append or remove methods. And a tuple is defined by using the regular brackets instead of square brackets. Otherwise, it works similarly to a list. So if we had L as the variable name for a list, let's call a tuple a T, and we define it using these regular brackets instead of square brackets, and we can put pretty much any data inside it. Or actually, we could even do a shopping list using a tuple by putting in this tuple some milk, some bread, and maybe some vegetables as well. Iterating through this tuple works the same way. So you could access these items using the slices and indexes, or you can iterate over it in a for loop. But the one thing you cannot do is to add or remove items, because once this has been declared, it's immutable. So a tuple is like a list, except it happens to be an immutable data type. The idea of using a tuple is basically it's like a list in all its properties, except if you know that the contents of that list will or should never change, you can make sure that it really never does change by using a tuple instead of a list. The only way you can modify a tuple is by creating a new one. So that's one variation of the list. The last data structure that we're going to look at is called a dictionary. Now, a dictionary gets its name from a real-world dictionary. You could also call it a phone directory if you want. The idea behind a dictionary, this data structure now looks a bit different. So it's rather than being a list of things, a collection of things, it's a collection of things with specific keys that help you retrieving those things or items. So you have some sort of short key, a word in a dictionary or a name in a phone book, for example, that help you find some specific values. So for example, a word in a dictionary helps you find the definition for that or translation of that dictionary word, or a name in a phone book helps you find someone's phone number. Well, if anyone uses phone books these days anyway. It uses the square brackets to store and retrieve items, just like the lists and some and tuples somewhat. And the uses of a dictionary are often the same as when you would need to use a real-life dictionary or a real-life phone directory. And as an example of a dictionary, the last code example is going to be a dictionary, and in particular, it's going to be a dictionary of. It's going to be an English Klingon dictionary. This has, I don't actually speak Klingon, but this happened to be an example I found online one day, so might as well do that. So I'm going to call this dictionary between English. So this dictionary is going to map English words to Klingon words. So I'm going to just call it en_KL, en standing for English and KL for Klingon for short. And how you define the dictionary. So if the regular brackets were or parentheses were used to define a tuple, the square brackets are used to define a list. These curly brackets are used to define a dictionary. And the values inside a dictionary, well, you need a pair of two things. We need one value that is going to be the key, and another value that is going to be the data item that you need. I'm not going to pronounce these Klingon words, but basically the idea here is that the Klingon equivalent for welcome is that. And if we want to print or to access some Klingon word using this index term that we have here in the dictionary, we can do that by well, putting it inside a print statement, of course, first. We can do that using the square bracket notation once more. And inside, we need the name of the key here. So if we do this, basically by inserting these English words as keys to the dictionary, we can print out the associated Klingon words. This is generally the idea. So by knowing the word in English, you can look it up in the dictionary in Klingon. To add a word in the dictionary, we can also use this same kind of square bracket notation. So we basically we can define keys on the go like this. So for example, for the phrase "How are you?" The Klingon equivalent is again, I'm not going to try to pronounce this, but it's that. And if we need to iterate through all the items in this dictionary, it works a little bit differently, but still using a for loop. So what we actually say is we want the English word, and we also want the Klingon words in this or in all the items inside this dictionary, which you do by using a special items method that the dictionary has. And then you can use both of these variables, the en for an English word and kl for a Klingon word, to print them both at the same time. So this hopefully should work. So we have this one word for welcome that we initialized this dictionary with, and this phrase "how are you" that we added later. So the reason why we need to iterate through this, well, actually we don't need to iterate through the dictionary like this. We could also just say for item in dictionary, and in this case the dictionary name is en_kl, and just print the items. But this works slightly differently in that once you run it, it will only print the keys to this dictionary and not the translations, or so only the keys and not this data. And the idea is that you can get easy access to these keys, but if you needed to access the data that this key points to, then you would have to access it using the square bracket notation. And again, this so this would be the equivalent of doing this manually. This special dictionary.items method does this for you, so it's a bit of a programming trick that does the same thing. These two should work identically, well, identically almost now. So this usual for item in dictionary gives you all the keys, and then using the square bracket notation you can retrieve the associated words from those dictionary keys. That's generally the idea. So for example, if you were creating a phone book, you might use names as a key for a number, or in some other context you might be using a number as a key for a name, depending a bit on what kind of an application you are or what kind of a program you need to complete. Right. So that, I believe, concludes the presentation for today. I am going to switch off the recording at this point.